Okay. So last class, we completed the design of sequential circuits. What is your objective is either you create a sequential circuit from a state diagram or you create a state diagram from a given sequential circuit. So you know now both the methodologies. There is a slight difference in only in the creation of the state table. You need to use the characteristic equation of the flip-flops that you are going to use. So today we will see another application of flip-flop, which is nothing but registers. Now, what is a register? Register is again a digital circuit which saves the data. Now, what is the digital device that will store a data? It is nothing but your flip-flops is the one that will store your data. Normally, if you look at the characteristics of a flip-flop, it can store only one bit of data. So if you want to save more data, then you must use more number of flip-flops. So a register is nothing but a group of flip-flops, each one which is capable of storing only one bit of information. So if you want to store n bit of an information, it means that you will require n flip-flops. Now, if you are using now 128-bit processors, right? Now, if you are using 64-bit processors, am I right? Few years back, we were using 32-bit processors. Now we are using 64-bit processor. What does this mean? What does this mean is each register that we have will have 64 bits combined, right? So which means it will have 64 flip-flops as one single register now. Okay, so you must have studied in microprocessors or microcontrollers what is a register is. Or where do you come across this particular term register? It is nothing but a notebook where people try to store the information, something like attendance register, something like the income register, which is used in kirana shops, right? So register is nothing but a device that stores information. Since we are looking at digital electronics here, a register in digital electronics means a digital device that is capable of storing information. Now, what is the digital device that is capable of storing information? It is your flip-flops which is capable. Hence, a combination of flip-flops, we call them as registers. Now, if you want to have an n-bit register, then you will require n flip-flops, which is capable of storing n number of bits. Normally, this register, this is not a standalone device which just has only flip-flops, right? Now, register is a device. If you, okay, for example, if you have an 8-bit register, you will require 8 flip-flops and it can store 8 bits. But register is, it consists not only the flip-flops, but it will also contain gates. So which means I will have n number of flip-flops. Say if I'm having a 4-bit register, I will have 4 flip-flops. Now, I might require at times that I must transfer whatever is this, the data from this flip-flop to this particular flip-flop, this flip-flop to this flip-flop, and this flip-flop to this flip-flop. At times what will happen is I might require my data in my 4th flip-flop here to 3rd flip-flop, from 3rd to 2 and 2 to. So which will perform these operation of shifting. We are going to shift the information, right? These shifting operations are normally performed using these gates that we are going to have. So what does this mean is a register will not only have flip-flops and it will also have gates. Flip-flops are normally used for holding the binary information and gates are usually used for transferring the data from one register to the other or one flip-flop to the other. Now let us consider a very simple 4-bit register. How does it look like? This is how a 4-bit register will look like. What does it have? This is a 4-bit register. So the number of flip-flops that you will require will be 4 flip-flops, which can store 4 number of bits. And we are going to use a D flip-flop. Normally registers, we will use only D flip-flops. We will not use JK flip-flop or RS flip-flop or T flip-flop. Why? Because we are not going to process any data. We are just going to shift our data from, or we are going to store our data. So the best one will be is a flip-flop that does not process our data. So the only flip-flop that does not process our data but just transfers or stores is your D flip-flop. Hence, D flip-flop is an ideal flip-flop to use it as a register. Okay, if you use T flip-flops, then what will happen? It will start toggling. If you give 1 here, you will get an output of 0 here. So we should not use T flip-flop here. So D flip-flops are the. So now what is the operation here? You will have your D input here. You will have your D input. Since we are having 4 flip-flops, let me call these inputs as D0 and output as Q0. D1, Q1, D2, Q2, D3 and Q3. So if I give inputs as I0, I1, I2, I3, I will get output as I0, A0, A1, A2 and A3. And when will you get this output? Whenever your clock pulse is active, right? So your clock pulse will be normally a square pulses like this, right? At a certain frequency. Whenever there is a rising edge of your clock, whenever there is a rising edge of your clock, these flip-flops will become active, and whatever the inputs that you are having, that will be transferred to your outputs during the rising edges of your clock. This is how a simple 4-bit register will work. Okay, now there are shift registers. You must have come across the shifting operation, right? A register which is capable of shifting the binary information held from each cell to the neighboring cell in a selected direction is called as a shift register, right? So a register is a one that will store the data, and a shift register is the one that will not only store the data, but will also shift the bits from one cell to the other cell in our desired direction or in our selected direction. Now, what can be the two directions that are possible? Either you can shift right or you can shift left. Okay. If you are very good at C programming, that you will know. If you want to take a modulus or you want to divide by 2, what you will do? You will shift right or left, right? If you are good at C programming, then you will know, right? Performing a division is normally done using the shift operation, and how that is performed in terms of a hardware. This is your flip-flops. You will give a control signal to the shifting operation of your gates, and your flip-flops will shift from one cell to the other cell. There are different types of shifting operation. Okay, so based on the data movement, your shifting operation can be classified into different types. First type is SISO type. What is this SISO? Serial in, serial out. And the serial in, serial out, either it can be a shift right operation or it can be a shift left operation. Now, what is a shift right operation is you give data to the most MSB bit. Yeah, that is most significant bit, MSB bit. And based on the control input across your shift operation, your data will move from in this particular direction towards right. And finally, you will get your data output also. And this is called as you are giving your input serially input, and you are taking the output serially out. So hence, this is called as the serial in, serial out shift register. Okay, I think I'm audible. Okay. Next is shift left operation. Now, what is shift left operation is your data input will be towards your LSB, and you will take your data output across your MSB, and your data will be shifted towards the left direction. Okay, so this is called a serial in. You again, your data is input serially, and your data is also taken out serially, and your movement of your data is towards the left. That is, the shifting takes place towards the left. Hence, this is a left shift operation. And there is a PISO also. What is PISO is parallel in serial output, which means your data will be fed parallelly across all your flip-flops. The cells that we have drawn here, these are nothing but one single cell, which means one flip-flop. So you input your data parallelly, but the shifting operation will take place serially and you will get your data output serially. Next is serial in parallel out, SIPO. What does this mean is your data is input serially and your output, the data is taken out parallelly. Something similar to this. This is called a serial in parallel out. And parallel in parallel out. Your input data is also parallelly fed and your data output is also taken parallelly. This is PI PO output. There are multiple different types of configuration based on the application. Okay, mostly these are used in memories, right? Wherever you want to fetch the data, you want to hold the data, right? So I hope you have studied a course on microprocessor microcontrollers or in computer architectures where you will have the data to be shifted out, data to be loaded, data to be moved right, left, right? So all these cases, we use registers. And then last two, rotate right and rotate left. What is this rotate right is the whenever this signal is active, this control is active, your LSB bit will be transferred to your MSB during the shifting operation. And your MSB will be shifted to the next rightmost cell. Likewise, your shift operation will take place. Towards your LSB and your LSB bit will be shifted towards your next leftmost bit. This is called as the rotate left. Now let us in detail, we are going to analyze these shift registers. The first one is SISO, serial in, serial out, shift right register. Okay, so we will take one by one. Okay, so SISO is a serial in, serial which will accept data serially and which will output your data serially. How is the configuration? Please first draw the flip-flops. This is my flip-flop 1, flip-flop 3, and flip-flop 4. Okay, now you know that flip-flop will have a D input and a Q output, a D input and a Q output. Okay, D input, Q output, D input and Q output. If I want to shift from right, my MSB bit here must move to my next most significant bit. So my Q output from my first bit register will be connected to my second second flip-flop's input. Second flip-flop's output will be connected to the third flip-flop input, and third flip-flop's output will be connected to the fourth flip-flop input. And finally, our output will be towards from our fourth flip-flop. So our bits are Q0 that comes from our first flip-flop, Q1, Q2, and Q3. So if you are giving after which clock cycle, you will get this particular one across your fourth bit. After 4 clock cycles, that is, you are giving 4 clock cycles. Okay, if I am giving say 101 here. Okay, now in the first clock cycle, what will happen? This is already fed with 1. Okay, let us presume. In the next clock cycle, what will happen is this 1 will get transferred to here. So 1 0 0 will be fed here and 1 will be there. And in the next clock cycle, what happens? 1 0 1 will be there. And in the fourth clock cycle, what will happen is, let me write here. So we are not giving any input here. So your input is going to be 0 1 0 1, and you will get your output when you are having your fourth clock cycles. Okay. Right. So this we can look at this shift register in a simple application, something like this. Let us assume that we are having two shift registers A and B. Please remember Whenever I say a shift register, it is a combination of multiple flip-flops. So I'm having a shift register A and shift register B. There is a serial input across my first shift register and there is a serial output across my first A register. Let me write SIA and SOA. This will be serial input of my B shift register and serial output of my B shift register. Both these shift registers are controlled by a clock. But at the same time, and why this particular feedback is given? This feedback is given so that we don't lose any information that we are shifting. So that there is a hold in our data. By this particular feedback, always our input will be available with us circulating in the shift register A. At the same time, this shifting operation can be controlled using a shift control, and we are going to use a gate along with our clock. What does this mean is clock is always a sequential part, right? Clock will be continuously sequential. But because of this AND gate here, this clock will be fed to these shift registers whenever you have the shift control active. So let us look at the timing diagram now. If we have our shift control active here during this particular phase, which means that AND operation of these two clock and our shift control operation will be your this particular clock output. So this clock output, please look at the values. See, this is CLOCK and this is CLK. CLOCK is a continuous square pulses and shift control pulses a rising edge clock towards these 4 clock cycles. So your clock output will be fed to your shift register only during this particular phase whenever your shift control is active. So you will have 4 clock pulses here for you to shift the operation. Now, let us analyze what is going to happen. Okay, so there is a theoretical explanation to the same thing. Now let me help you in explaining how this is going to work. Just a minute. Okay, so this is your shift register, and let us assume, right? We are having 4 different clock cycles that are active here, right? So at T1, T2, T3, and T4 are the 4 clock pulses that are going to be active, the rising edge clocks. So let us presume that my shift register is having my initial value as 1011 and my shift register B is having 0010 and my SO output across my B shift register, that is this input. Okay, I don't want to scroll up and down. That is why I have saved it here. So this particular output here, SO, will be this column. Okay, now we are having 1011 and 0011. After T1, what does this mean? This is the 4 clock cycles that are going to be active. This is T1, this is T2, this is T3, and this is T4. During T1, what happens? Your most MSB bit will be shifted towards here, and the 0 will be shifted here, and this 1 will be shifted here. But at the same time, please remember, okay, I should not scroll, right? So at the same time, please remember that we have given a feedback here also, right? Which means that our LSB bit here will be shifted to our MSB. There is a feedback here. So the one that we were having here, it will be shifted towards our MSB here. At the same time, it will be shifted to our shift register B also. Okay, so that is how it is, right? It is saved through our feedback to our MSB, and at the same time, it is shifted towards our shift register B. Okay, now what will happen to the contents of your B register? We were having 0010. Since this is a shift right register, the 0 will be shifted towards the next MSB 0, 1, and this 0 will be obviously that is what is available already across our SO. And now after T1, this 1 will be shifted out. Now during T2, during the next clock cycle, what will happen? this 1 will be shifted here. This 1 will be shifted here. 0 will be shifted, and this 1 will be fed back here. And at the same time, this 1 will be fed back here also. This 1 will be shifted here. 0 will be shifted. 0 will be shifted, and the 0 will be our output. Similarly, after T3, what happens? This 0 will be based on our feedback, and at the same time, it will go to a shift register B. This 1 gets shifted here, 1 gets shifted here, 1 gets shifted, and this 1 gets further shifted, and this 0 will go as an output. Okay, so this is how your shift registers will operate whenever based on your clock cycles. Understood how this simple application is working? Any doubts? Okay. Next, what we will see is we will see serial in, parallel out shift registers. Just a minute. Okay. Now, serial in, parallel out shift registers. What does this mean? My input must be serially fed. I must take my output parallelly, data parallelly. So this will accept the data serially, and your output will be available across all stages simultaneously. How you can employ? Simple. You are having a D flip-flop. Okay, I've left here. There will be a clock signal. So you will be feeding your data input. So from first flip-flop, you will have it across your second flip-flop, second to third, third to fourth, and your last bit also here. At the same time, since this is parallel output, you will take your Q0 output, you will take your Q1 output, and you will take your Q2 output here. So this is your serial in, parallel out shift register. Now what will be, now can you draw parallel input and serial output, right? So parallel input will be how? Let me reuse this particular diagram. Anyway, I have a fresh diagram below, but I will explain it here. Parallel input serial register, right? Parallel input means I will be feeding D0 here. I will be feeding D1 here. I will be feeding D2 here, and I will be feeding D3 here. Then what? Serial output. Serial output means obviously this has to be fed serially here. Okay. So how? You have to activate your clock. So slightly it looks complicated, right? I'll explain how. So now in parallel input shift registers, you have to do two operations, and those two operations cannot take place simultaneously. What are the two operations? If you are giving a parallel input, which means that you are loading the data. Okay, every clock cycle you have to load the 4 bits. At the same time, you are doing a shift operation also. So you are doing a loading operation, and you are doing a shifting operation. Now, when loading is taking place, you cannot shift. When shifting is taking place, you cannot load, which means that loading and shifting, they will be a complemented operation. So that can be affected by using like this. Okay, just listen carefully here. Whenever I'm shifting, right, this particular line will be active. Whenever I'm loading, this particular line will be active. Okay, now please remember, I have to load my data parallelly, and this can be affected. So let us assume that first I'm going to load my data. So my loading will take place if I have 4 flip-flops like this. How do I parallelly load? I will load my data parallelly like this. But this loading across these 4 inputs has to be controlled by a load input, right? So hence I'm using it through a AND gate here. I'm using it through an AND gate here. Okay, this is, so what does this mean? Only green line is active, these gates will be active. This gates will be active only when this green line is, and I can feed my data directly into my flip-flop, directly into my flip-flop. Okay, my data will be available, so I can load here. For the first thing, you do not require, but anyway, whether this is serial input or parallel input, you are just going to load, right? So now what will happen that this is not active. This yellow one is okay. Oh, I have to erase this. It's not good. Okay, I'm unable to erase. Okay, forget about it. Okay, so which means that the shift is not active now. Okay, only this green is active. Green is active in the sense loading is active. So loading is done parallelly. Now, once you load the data, what does this mean? I will have some data here. Okay, let me write, say, if D0 is 1, 0, 1, 1, then this loading is high, right? Which means that this is high, and whatever is this particular output, so 1 will already be here, and 1.0, 0 will be transferred, and since this is an OR gate here, so you need not bother, whatever it is based on this particular input. And what is this particular input? This is 0 here, and if this is 0 and the output of AND gate is this will be 0. So 0.0 will be 0, which means that the same output will be coming here. And this is always 0 because this is active low. This is 0 and this is 1. 1.1 will be 1 here, and 1 plus 0 was 1 here. So this is going to be 1, this will be 0, and 1 will be loaded. So what is loaded here? This is 0 is loaded here, 1 is loaded here, 1 is loaded here. So you have loaded 1, 0, 1, 1 across all your flip-flops. This is what is the loading operation is. Now, shall we look at the shifting operation? Before that, let me erase, if erase is working. Oh, why? I don't want to erase everything. Yeah, it's okay. So now let us do the shifting operation. For shifting operation, okay, it's okay. Let us erase the whole part. Okay. All right. So we have 1011. When I have to shift, which means that my shift will be 1. This line will be disabled. This will be 0. If this is 0, gates are 0, 0, 0. Your output is 0 here. 0, 0, 0 here. Okay. Now, when this is 1, this gate is 1, this gate is 1, this gate is 1. Now, since this is 1 here, 1.1, 1 will be transferred here, 1 will be here, and a new value, let me write here, a new value will be 1 here. Here it is 0, so 0, 0.1 will be 0, and this will be 0 plus 0 will be 0, so a new value 0 will be there. Okay, now the old value is 1 here, so 1 will be fed, 1.1 is 1, 1 plus 0 is 1, so a new value of 1 will be there. Now look at the values. Look at the values. If say for example we are loading D0 to B0, so a new value 0 will be there. So this 1 is shifted here. This 0 is shifted, and a new value 0 is shifted here. So we have shifted, right? So this is how you use a shift and a loading operation using this particular logic. Okay, because we are going to use this particular logic extensively now. Okay, I hope only if you understand this, then you can build upon this particular logic. I hope you have understood. Okay, any doubts? Okay, now uh, the Boolean logic expression, if you look, the Boolean expression for these inputs. The Boolean expression for these input is nothing but what? This line is shift line, right? Shift ANDed with Q0, which is ORed with, this is your load bar. So load bar, I can write it as shift bar in fact. So shift bar dot D1 will be the Boolean expression for this particular line. Likewise, you can write the Boolean expression for others. So why did I write this Boolean expression? Just to understand mathematically also. That is, if your shift is 0, then what will happen? If this is 0, this will be 0, this will be 1. So D1 is simply loaded. If your shift operation is 1, then this will be 0. So your Q0 is shifted. Okay. So D1 is your parallel input, Q0 is your serial input. So just to explain you the Boolean operation for just one input, not for the every input here. Based on the Boolean operation also, you can understand how the loading and the shifting operation is taking place. When your shift is 0, your D1 is loaded. When your shift is 1, your Q0 is shifted. Okay. Now, now let us look at parallel input, parallel output register, which is fairly very simple. So what is this parallel input and parallel output? I'm going to load it parallelly here. So D0, D1, D2 and D3, they are parallelly loaded, and you have to take parallel output also. So just take parallel output here. Only thing that they are controlled is through the clock here. Through the clock, they are all synchronized. Okay. So this is a parallel data inputs are here, and parallel data outputs we are taking out. Okay. Any doubts? Okay. Now comes slightly an additional application of this shift registers. What did we do here? We shifted right. Am I right? We loaded and shifted right. There is another kind of shift registers which is called as bidirectional shift registers. When I say bidirectional, what does it mean is your circuit must be capable of shifting both right as well as left. So if you are shifting right, then you cannot shift left. So shifting right and left must be a complemented signal. Okay, and we are going to use the same logic here. Okay, only thing is we will not load it parallelly. Okay, so let us use the same logic. This is how your shift right and shift left operation. First, let me explain you the shift right operation. Okay, so right and left are complemented inputs. Right and left are complemented inputs. So when this, which means that you have wanted to shift right. When this is 0, you wanted to shift left. When it is 1, so which is the line that will be active? This is the line that will be active. Okay, so and which is the line which is not active? Not active. So 0 input will be there. So a 0 output. If this is 0 here, this line will be 0. Your shift left operation will be 0. Shift left operation. Okay. Now when shift right is active, this will be 1. This line will be 1. This line, this gate input will be 1, and this gate will be 1. If you want to shift right, what does it mean? One data must go to 2, 2 data must go to 3, 3 data must go to 4, and 4 data will obviously go out. So if so, you have to give a serial input here. If I'm giving a serial data here, and this is one, what are gates that are going to be active, and your OR gate will be obviously will be active, which will be fed to D1. And at the same time, this input, whatever you had, this gate will be active. Obviously, OR gate will be active, and then this data will be fed here. And similarly, your Q data will be fed to this particular gate. Your OR gate will be active. This data will be fed to the third flip-flop, and from third flip-flop, it will be fed to this gate, an OR gate, and through the flip-flop, and then you get this output. So you see here that there is a shift right. Now, how is the shift left operation will take place? Any doubt in the shift right? Shift left will require slight modification in the circuit. Shift right is okay. Okay. Now let me explain shift left operation. When it is left operation, what are the gates that will be active? So this line will be active. If this line is active, this flip-flop, these gates are going to be okay. So which means a zero input will be fed to the right flip-flop. This is not going to be active because this will be zero here. This is not going to be active. This is not going to be active. Now shift left, right? So if I want to have a shift left, then fourth data must go to 3, third data must go to 2, and second data must go to 1. So fourth data, so which is the flip-flop that will be, which is the gate that will be active and which is fed as an input to my third input. So my third input will go through this particular gate, which means that I have to feed my Q3 output to this particular gate. Similarly, can you tell me where from 3 to 2 will go? So my input to 2 will be through this particular AND gate, and my output from Q2 will be fed to this particular gate here. Similarly, what will be where the input to my first flip-flop will be through this particular gate, and my second output, which is Q1, will go to this particular gate. And at the same time, where will you need not bother about what will happen to this particular input, because we are not rotating, but we are just shifting. If it is a rotate operation, then what you will do? This Q0 output now will be fed to, I'm just drawing roughly, will be fed to this particular input. Where is this input going? Yes, it will go to this particular input now. If it is a rotate right operation, sorry, rotate left operation. Okay, so this is how you can shift your data right or left based using these particular shift registers. Any doubt? So this is called as a bidirectional shift register. Okay, so and these are the explanations that are there. And for the sake of understanding, this has been used using a shift register. Okay. Right. So I've already explained this particular part. Okay, so I've already explained this particular part. That is what happens to that is a Boolean expression has been written for each input. Okay, so the inputs to the flip-flop, right? So what is the input to this particular flip-flop? This is your serial input ANDed with what? ANDed with your write operation, right? Serial input ANDed with write operation, which is ORed with your left operation, or left is in terms of the right bar, and which is ORed with what? Which is ORed with Q1, which is ORed with Q1. Right. Likewise, you write all the Boolean expressions here. Now, whenever your right shift is taking place, what will happen when your right is 1? This will not be active. This will not be active. This will not be active, and this will not be active when your right is 1. So what will happen? Your C1 will be available here. Your Q0 will be available, Q1 will be available, and Q2 will be available. When your right is 0, then it is the reverse. Let me use a different highlight. When your right is 0, this will be active, this will be active, this will be active, and this will be active. So, and this will not be active. Okay. So this will not be active. These things will not be active when your right is equal to 0. So what you will have? You will have Q1 here, you will have Q2, Q3, and your serial input here. Now look at the sequence here. So during your write operation, your serial in is fed to the first flip-flop. Your Q0 will be there in the second flip-flop, your Q1 will be there in the third flip-flop, and your Q2 will be there in the fourth flip-flop, which means that you are shifting serially right. Similarly here, if you look at the sequence here, when your right is 0, which means that left operation, your serial input will be available across your fourth flip-flop. Then your third flip-flop will have the Q3 output likewise. Okay, so I've already explained you, but still you can have a look at it. Okay, so next we will see an universal shift register. Now, what is an universal shift register is, I will try to explain till we have our time, and because this requires slightly a longer explanation also. Okay, sorry, there was a disconnection. I will rejoin. Okay, I will reshare the slides. Okay, I hope my screen is visible. Okay, now now if the register is okay, now if the register has both shifts, both the shifts, that is right and left, and the parallel loading capabilities, they are referred to us as universal shift register. Okay, now we are going to design this universal shift register only. What is that you need to have an universal shift register? Or you will basically need four D flip-flops, right? You will require four D flip-flops for shifting the registers. In addition to that, in order to implement these capabilities, what are the capabilities? Shifting right, shifting left, your parallelly loading capability, and then yes, and okay, these are the three different operations that are required. So how do you implement this? The best possible way to implement all these particular four operations is couple these D flip-flops give the instruction to these are instructions. Give the instruction to these D flip-flops using 4 different multiplexers. I'm going to have a 4x1 multiplexer. Okay. So each one is a 4x1 multiplexer. When I say 4x1 multiplexer, how many inputs I will have? I will have 4 inputs. Each will have 4 inputs. I will tell you the logic now, then I will explain. If I have 4 inputs, how many select lines I will have? I will have 2 select lines. S0, S1 will be the select lines. Each one will have two select lines. Now, what are these inputs now? These inputs will give instructions whether to shift right or shift left or parallelly load. So I can give, say, shift right to be a value of 0, 1, shift left to be 1, 0, parallelly loading to be 1, 1. And what about 0, 0? Let it not do anything. So no change. Okay. So 0 in, if you are giving a 0 input here, nothing will do. It will just have its input as it is. D flip-flop will have its input as it is. Now, where will be the output of these 4x1 multiplexers? This is a 4x1, right? So these are the inputs. All these 4 lines are your inputs. And where will you have your output? Your output will be fed to your D flip-flop. Your output will be fed to your D flip-flop. Okay, so based on the instructions now, so when it is 0, all you need to do is your D flip-flops, please remember that this is D0, D1, D2, and D3. What will be the output of your D flip-flops? Q0, Q1, Q2, and Q3 will be the outputs of your D flip-flop. Okay, so I hope you have understood till this. Because if I show you the complete circuit, you will get scared. Okay, so that is why. So what we have done is, for an input of 0, 0, we have just connected our circuit. Okay, so I do have a drawn ready-made available to you. So this is what is a 4x1 multiplexer is. The output of a multiplexer now will be fed to each D input. Okay, understood? Okay, right. So my screen is visible now. All right, now let us look at the second operation. What is the second operation we have decided? We have decided that S1 and S0, that is 0, 0, I will not do anything, no change. Before that, we looked at the other inputs also, a clear input and a clock input. If I want to have, if my clear input is active, because I want to reset all my flip-flops, then this clear input must be fed to all the flip-flops here. Okay, so how do I draw? Okay, so assume that it is behind. So my clear input is connected here. My clear input is connected. Why I'm not, I can draw it like this also, but I'm going to have a lot of lines coming here. So that will create a confusion. So I'm not, just presume that these lines are running behind this. Maybe a dotted line will help. Okay, these lines are running behind the flip-flops. Okay, they are all connected. So whenever my clear input is active, all my flip-flops will be reset. Now, what about the clock? I will have a clock also. So my clock input obviously will be given. It is a synchronous clock, so it will be available across all my flip-flops. Now, okay, right? So my clear input is there, my clock input is there. Now, when it is 0, 1, my flip-flop is when this S1 and S0 are 0, 1. And okay, what will happen to this 0, 0? When it is 0, 0, my inputs will be as it is, right? So I will have no operation across this 0. Okay. All right. Now it is shift right operation. When it is 0, 1, what will happen is this particular 1 will be active. What are the signals that are going to be active? This will be active. This will be active. This will be active. This will be active. I should do shift right operation. When it is 0, 1, I must do shift right operation. What is this shift right operation? That is whatever I have it in my first flip-flop must go to my second flip-flop. So my first flip-flop will go to my second flip-flop, that is this particular signal will be active. Likewise, my second flip-flop's input will go to my third flip-flop. Why I'm connecting it to 1? Because whatever it is available across 1, I will have it across my output, across my multiplexer. Hence, I'm connecting it to 1. So whenever my 1 is there, okay, similarly, my third flip-flop will be fed to the fourth flip-flop. So this is my shift right operation. Okay. Now, what about 1, 0? When it is 1, 0, it is your shift left operation. What do you mean by shift left operation? Whatever I'm having it here will be fed to my third input here, second input here. Whatever I'm having it across my third and fourth third flip-flop has to go to my second flip-flop. So this particular input will be active. All right. Now you have understood how, right? So this is a very simple logic. The same thing that we are, let me explain it using. Okay, so we have shift right and shift left. Now the parallel loading. When it is 1, 1, you must parallelly load your inputs. So since this is time, we will look that parallelly loading case maybe in the next class. Okay. Any doubts? So if you have any doubts, you can leave the class.